Okay, so today we're going to go over Maxwell 3D simulation. We're going to run through an example project. Um, and we're in this simulation, we're going to be looking at the mutual inductance or coupling coefficient between two identical coils. One is going to be a transmitter and one will be a receiver. Okay, so assuming you have ANSYS open already, and also we're using ANSYS R19, which is also version 2018.0. So create a project, and then within there you insert your design, which is going to be Maxwell 3D design, and we can name this just name it video demo. And you can see here, in the parentheses, if you see video demo magnetostatic, that's what we're going to be using for this video. And this is essentially saying, we're going to be looking at magnetic fields generated by it's a DC current, and we're not trying to look at anything that's frequency dependent, such as current density or induced currents or anything like that. So to start, we'll create our first coil, which is going to be a transmitter. So under draw, we have user defined primitive, segmented helix, and from there, actually I take that back, we're going to go to examples, rectangular spiral, Python. And from there we have this prompt. Let's see, we have a description for each thing. But we're just going to do an arbitrary coil design for this. So let's start with, let's do 10 turns. And our thickness is going to be roughly 2 ounce, equivalent to 2 ounce copper. So that's about 3 mils. We do that. And then the trace width itself is going to be 3 millimeters wide. And the distance, which is distance from the inner edge of one turn to the inner edge of another turn, is going to be 6. So that equivalently means if you take distance and subtract width, that is going to be your actual pitch. So it's going to be 3 millimeters. And see, we have the coil here generated. Let's just change this to copper and change the color to orange, because why not? Okay, so from there, what we're going to want to do is create a region. So, sorry, 1 second, my mouse appears to be having some issues. There we go. We're wanting to create a region where we're going to simulate our simulation is going to take place. So typically, what we're doing is a cubic meter region. So you tab into the bottom right, and you have your first point of your cube at -500 all around, and you make it 1,000 by 1,000 by 1,000 millimeters, so 1 cubic meter. Well, here's our region, and we can just name it region. Let's rename our coil to TX, and from this region we can make it transparent. We're actually just going to minimize it for now. So for magnetostatic designs in Maxwell 3D, you need to have, I guess stepping back even further, to generate your magnetic field, you need a closed loop of current, or at least a loop of wire which has current going in and going out. And within Maxwell, it turns out that the current, the face of the face in which the current is being applied must be also at the edge of your region, which is this meter box. So our coil's pretty small. I think it's probably about 6 centimeters or 12 centimeters wide, and our box is a meter wide. So we need to have basically leads extending all the way to the end of this region. So we're going to do that now, and basically we're just going to create some copper leads right here. Let's say it's 1 by 1 by 2 millimeters, and then we're going to have one over here, 1 by 1 by 1, negative 1 by 1 by 2, sorry. And from that, we're going to extend them to the negative y, because that just seems kind of intuitive. That will be where these leads are flying back to. So we just have to generate that really quick. We're in the X, we're going to want to make this in the XZ plane. So yeah, just making the little box here. And right now we're just going to, we don't know the exact distance to the edge of that region, so let's just overcompensate and say it's 600 millimeters away. So have that lead. And then for this lead, we're going to do the same thing, but we're also wanting to make sure that our leads are not touching. So let's make this slightly smaller than 1 millimeter, like 0.75. And this will be also negative 650 just to be safe. Let's say negative 700, why not? And you can see here, one thing to keep in mind is you're wanting to keep for these leads, considering, if you consider them to be parasitics, you don't want to increase parasitic inductance more than it already is. So that's why we're wanting to keep these leads as tight, as tightly wound together as possible. Okay, so we have these leads. Let's unite them to the coil. So I'll just create the TX, and we're going to control click the remaining 4 and then hit join or unite. So we have a continuous coil, and then we have our region, which is right here. Make this visible. So we're not wanting the leads to extend beyond the region, though. You need the leads to end on the face of the region. So one trick you can do, you see there's some overhang here. So one trick you can do is you create a second box that has one face shared with the face of interest on your region. And then you take your coil, you select TX, and then you select box 5, which is this new one, and you subtract box 5 from it. So that basically trims your leads to be on the face of your region, as you see here, perfectly trimmed. Okay, so that's the TX. Let's minimize this. So we're running a receiver as well, because the point of this simulation is to see mutual coupling between two coils. So what we're going to do is we're just going to edit, right click, hit edit and copy, and then we're just going to hit paste. So let's rename this to RX, and let's move. We're wanting to, let's say we want to see the coupling in the z-axis. So we're going to want to move this, tab into these coordinates here and say, let's just say for now, let's move it 50 millimeters. So you have your RX, which is a nice blue color, but we don't want it to be just 50 millimeters above the TX. We want it to be parametric, because we're interested in how the coupling changes as a function of distance. So if we create a parameter or variable called z space, we can make this a length unit in terms of millimeters, and let's say default it's 100 actually. So you see here, if we go to the properties or project, if we make it 50, you can see it, the changes immediately reflected in the design. So, and the leads also follow along, because it's a continuous coil. So okay, let's see. So from there, we're wanting to add, we're wanting to actually apply an excitation of current excitation to both of these coils. So they both have are generating their magnetic fields. So if you hit F, it's a hotkey to select faces. You will right click on the face of interest and say assign excitation and go to current. This is TX in. We're wanting it to be, just make it variable I in case we want to control it or change that down the road. And of course, this is peak current. If you're wanting to convert to RMS, you just have to apply, divide by a square root of 2. Okay, and then so you see we have current going in, and now we need current going out. So assign excitation, current TX out, and then I, but we're going to want to swap direction by clicking here. So you see you have current in, current out. So we're going to want to do the same thing for the RX then. This is just a matter of time to apply this. RX in, I. Then we're wanting assign excitation, RX out I swap direction, so it's pointing outward, and there we go. Okay, so from there, we're going to open this parameters tab and assign a matrix. So basically, this is matrix is it's nice to create a matrix especially when you have multiple, more than two coils. So if you're interested in the mutual coupling between TX and RX1 and then TX and RX2, you'd be creating two individual matrices. But here, we just kind of have, we have two coils, so we're just going to group them together, and it will generate a basic 2x2 matrix when we're looking at things such as mutual inductance or coupling. We have parameters, and then from here we're going to want to generate our mesh. And also, I forgot earlier, we are going to want to also create a region, which is basically skin tight onto this region we already created. It's explicitly called region, because right now this is just a vacuum box named region. So let me actually rename this to avoid confusion. This will just be vacuum box. We're going to create a region that is padded 0% relative to the biggest object in this simulation, which is the vacuum box. And there we go. So you can see they're identical. But this is necessary to run the Maxwell 3D magnetostatic simulation. Just minimize this. Okay, so for mesh operations, right-click the vacuum box, and then we're going to assign a mesh operation inside of the box, because that's where we're interested in. We're running the simulation to look at the fields and coupling within that box. So we could just call this box mesh. Leave it the default setting of 200 millimeters for max element length. And then for both TX and RX, since they're identical, we can just click both of them and assign a mesh operation on the selections that are length based. And it's let's just say 100 millimeters. Let's make it a nice round number. So this will be coil mesh. We have two mesh operations. We should be good there. And then if we go to analysis and create a solution setup. This is something I've gone over in previous videos, but number of passes is something that you really cannot be certain of until you run a few simulations, and it's also dependent on what percent error you're running. I ran this one a couple minutes ago, and we saw that it was having trouble hitting 5% error within 10 passes. So if we just bump it up to 10% error, we'll be okay. But if you want to go down to 5% error, you should look at increasing your max number of passes to maybe 12 or 15, and it's inversely proportional to one another. And convergence, let's just say we run at least 5 times, because we know it's not going to converge until at least maybe turn past 9 or 10, and then we'll be okay with one converge pass for now. So this expression cache, this is something noted in other videos as well, where until we hit OK and initialize this solution, the solution setup, we can't come to this and create another cache to look at as a function of pass. So we can come back to that in about a minute. For solver, we're going to want to enable iterative solver, which is a little bit less intensive on RAM and memory usage. And if you're using like HPC or a server solution like Nimbix or anything, you'll be okay with leaving this unchecked. But if you're on a personal machine like I am right now with limited RAM, you might want to select this to lessen the burden on your computer. Okay, so and then from there, as I said earlier, we're interested in seeing how the coupling changes between these two coils as a function of the spacing of the RX to the TX. And our variable there is Z space. So we're going to add a parametric sweep, like a parametric sweep for Z space. And let's say it goes from 50 to 200 millimeters and the steps at 50. So we're going to have 4 different positions that we're interested in. And for each of those, we're wanting to calculate, we're interested in the coupling coefficient, which is between Tx and Rx or Rx and Tx. They're identical due to reciprocity. Add that. And options, don't forget to click the box that will save your fields and mesh, because that is necessary for these calculations. And also one more thing, say we're curious about what the field strength looks like, in the form of a heat map at some distance. So let's just create a sheet. Let's say it's right in between these coils, and let's say it's 100 millimeters wide, totally flat. Oops, I'm sorry. Let me redo that again. So -50, -50, 50. From that, it will be 100 millimeters, 100 millimeters. That's 0. I appear to be doing something wrong. Oh, sorry, I'm in the wrong plane. That will do it. Okay, sorry about that. Let me redo it now. Negative. Yep. Sorry, I'm having technical difficulties. 50, 50, 50. And it's going to be 100 by 100 millimeters and flat. So there we go. All right. So here's a sheet that we can make it non-model because, it's not really, it's not going to really impede or interfere with the coupling whatsoever. It's just a 2-dimensional sheet with no material properties, but we can just make it a non-model object and make it sort of transparent so you don't forget that it's there. And then also what we're going to be looking at is going to be, if we go to results and create a plot, we're going to be interested in the coupling coefficient as a function of spacing. So create new report, and there we go. This is going to be coupling coefficient versus spacing. So that will, update itself as the simulation is being run. And also, once the simulation is already done and we're in post-processing, we can right-click, click on this non-model rectangle, and let's call it B field sheet. And say we want to look at the B field for it. So we right-click, go to Fields, B, Mag B, and we just hit Done. We don't have to select anything else. And once the simulation's completed, we'll be able to visualize the B field on that sheet in a heat map. So one more thing of note before we look at the results is if we're wanting to move this in a direction that's not the Z or X, say we want to move it in the Y, this is going to mean that your leads are going to not be touching the edge of your region anymore, and that will result in an error. You won't, your simulation will be aborted the moment you try doing that. So to mitigate that, you'll either have to do like a parametric design on these leads, which are dependent on the distance and Y you're moving. So you want to ensure that this face is parallel to the face of the region. So that's just one thing to note, to be careful about if you're looking to do a simulation similar to this. So yeah, I actually already ran the simulation. So if we go, or really quick, I guess you just have to validate, make sure everything's okay, and then you just hit Analyze All. So I already ran this about 20 minutes ago, and here's the completed version. And basically, if we're just looking at coupling coefficient, which is right here, we see if the x-axis is the distance between Tx and Rx, you can see that the coupling coefficient does have a kind of a 1/x curve to it or behavior to it. It's fairly low resolution because we're doing steps of 50, but you can see that there's this obvious nonlinear decay, and that does make sense. If you plot the B field as a function of Z, you'll also see something similar. So it makes sense that the magnetic energy captured by the receiver is decaying at a rate of 1/x or more. And from there, we have one more thing, and it's the sheet, B field on sheet, and you'll see here that this is a logarithmic scale, but you can see kind of the field intensity as a function of distance. And if we wanted to, we could also move this guy around or have it. It's a non-model object, so you can move it around however you want, even after the simulation's been run, and you don't have to rerun anything. So yeah, that's basically all I here to show you. I hope it's been informative, and yeah, this is Maxwell 3D.